All right, folks, here we are, Modern Physics, Part 2, Dual Nature of Light. So now we're going to go a little bit deeper. If you recall from last time, Einstein came up with this concept that light is both a wave and a particle. It's simultaneously the exact same thing. If it helps to think of light as a wave, think of it as a wave. Treat it with wave-like equations. If it helps to think of light as a particle, think of it as a particle and use your particle equations. So now what do we do from there? Well, this was 1905 when Einstein published that paper. And at that point, the world exploded. This new component of modern physics just threw people for a complete loop. Einstein was on the cover of Time magazine. He was a household name. In between 1905 and 1922, you had World War I, aka the Great War. But there was also a lot of research coming. We're not Depression era yet. This is 1929. So we still have a lot of research going on. Now, this American chap, Arthur Compton, came along and he said, all right, well, let's take a look at this. Einstein's photoelectric equation, if you go back to that thing or look at your formula sheet, it says Ke max equals HF minus W naught. What's with that max? I intentionally neglected mentioning that in the previous video. Well, it turns out, let's watch this little animation here. Coming in from the left is a little particle of light, a photon. It's a wave, it's a particle, hits an electron and knocks it off into space. Okay. Previously, what happens is that particle of light comes in, hits the electron, and the particle just disappears. It's like throwing that softball at the pin. The softball comes and hits the pin, and boom, it's gone. And now that pin just goes flying off, and it's as if the softball was never there. That's a basic premise of Einstein's photoelectric equation. Just, hey, off it goes. That photon of light was completely absorbed into the electron, disappeared on you. Sometimes that doesn't happen. And it's kind of like a ricochet shot. So you throw the softball at the pin, and the softball goes deflecting one way, the pin goes the other. That's what you're seeing happening in this animation. But clearly, if energy can either be created or destroyed, what's happening is that new photon that comes deflecting off has to have less energy. It gave some energy to the electron. That's what caused it to move. So Compton kind of went along with it and said, okay, got it. Let's look at this and say E equals HF, our basic energy of a photon, C equals F lambda, combine together and you get your E equals HC over lambda. So that in mind, notice again down the bottom here, that animation we had in the previous slide, when that photon comes and hits the electron, notice what happens to its wavelength. I'll let you look at it again here. Tiny little wavelength coming in and a long wave coming out. And if you look at our equation E equals HC over lambda, if wavelength goes up, energy has to go down. And that's exactly what's happening here. So this is showing another energy conservation type setup here. Further solidifies the idea that light is a particle, because particles, when they bang into each other, conserve energy in some form or another. We normally talk about momentum with collisions, but if no sound or heat is produced, which is what's happening here, energy is conserved as well. And this shows a perfect energy conservation. If we go back to that second video I showed you with the 10 equals 8 minus 2, the kinetic energy ejected electron equals 8 minus 2. Well, this would be a little bit different because the kinetic energy electron wouldn't be equal to 10 equals 8 minus 2. I'm sorry, I said that backwards. 8 equals 10 minus 2, you would have instead one additional element to that equation, which is, hey, there's this new little photon that also has a little extra energy. So it's almost like writing a chemical equation. Things balance out on the left and the right. You would just be adding another term to this one, saying, yes, you have an electron kicked off with an energy of 8 plus an initial photon that has some other energy, let's call it 1. And then on the other side, the math works out for you. Okay, momentum. We remember momentum from earlier in the year. Einstein not only did photoelectric effect, but in 1905, he also wrote the E equals mc squared, relativity stuff. And with that, you can derive these equations where you say momentum equals energy divided by the speed of light. Don't really want to go into it right now. But in doing so, if you do some substitutions, we've learned E equals HF. You know C equals F lambda, and you come up with a new equation for a photon, which is P equals H over lambda. Our problem is this: we don't have from before P equals mv the ability to use that equation with photons. Photons don't have mass. You know that. I know that. Light doesn't have mass. We can't pick up mass and set it on an electronic scale and see how much mass it has. It has nothing. So it's a particle, it's a massless particle. Well, what would be the momentum of a massless particle? This equation shows us, which is P equals h over lambda. So that's the momentum of a massless particle, otherwise known as a photon. Pretty cool and an ingenious way to work around this thing. Now, Louis de Broglie, a French guy, comes in, and Louis de Broglie says, hey, wait a second, you notice the timestamp here is a little bit later on. This is 1924. And he says, P equals h over lambda. Let me study this a little bit. By the way, you see a stamp in the bottom corner. His dad was a famous scientist. So this French guy is trying to fill in the shoes of daddy and come up with some cool ideas. So this guy's coming in, he's saying, all right, we've got this recollection of what was happening here. P equals h over lambda from Einstein. Well, if waves, i.e. light, photons, are particles, well, if waves are particles, well, then particles must be waves. All particles have to be waves. If waves are particles, then particles must be waves. It's got to go both ways. You can't have just it go one way, it's got to go both ways. So that means all particles, like you and me, we're waves. You could have a golf ball. Golf ball is a wave. All these things are waves, and that's something everybody's going to scratch their head and say that doesn't make any sense. But what would be the wavelength of these big particles? Well, just take the equation that we saw from Einstein, P equals h over lambda, rearrange it for lambda, and there's your wavelength. Wavelength equals h over p. Now, this sounds insane, absolutely insane. So let's dig deeper and see what's going on here. Let's try the de Broglie, or us dumb Americans will just go off and say the de Broglie wavelength. Calculate the de Broglie wavelength of an electron traveling at 1.0 times 10 to the 7 meters per second. So what's the wavelength of this electron? We've got the velocity there. How can we do this? Well, let's see here. Lambda equals h over p. So we know from first semester, P equals mv. If we know the mass of electron, which we can look up, and we know the velocity of electron, and we know Planck's constant, we can do this. So take the numbers, 6.6 times 10 to the negative 34 joule seconds is Planck's constant. Here's your mass of an electron. We did that back in quarter 2. Here is your velocity. I don't know where the superscripts went, but that's it right there. If we plug it all into the equation and we solve for wavelength, the wavelength of this electron is 7.3 times 10 to the negative 11 meters. That number is really small. Doesn't mean much to me, doesn't mean much to you. The diameter of a small atom is 10 to the negative 10 meters. So this is a tenth of that. We can't measure this. This is just way too small. We can't come up with any solid defining evidence. So let's try something else. Let's try something bigger, not an electron. Let's do a baseball. So let's throw a baseball here. Baseball's mass is 0.4 kilograms. Let's throw it at 90-something miles an hour, which is 43 meters per second. Let's see what the wavelength of this would be. So play the same game again, write lambda equals h over p, put in h, 6.6 times 10 to the negative 34. Here's your mass of your baseball. Here's your velocity of the baseball. And what do you end up with? 10 to the negative 35 meters. Now, if it's not humanly possible to grasp 10 to the negative 10 meters for most people, including me and you, 10 to the negative 35 meters is ridiculously small. So if a baseball is a wave, we could never, ever, ever measure the wavelength of that baseball. We don't have the tools to do that. We're never going to see that happen. If the pitcher throws the ball towards the mound, you're not going to see the ball waving up and down and up and down and up and down as it goes. It's just too small. So we've got a problem here. We've got a real problem that we can't take big particles and like you or me or baseball and see these wavelength properties. So the proof, there's this crazy French guy, Louis de Broglie, who said that, yeah, we've got all particles that must be waves. Well, a few years later, Davison and Germer, two American guys, come along and say, well, let's think about this thing. If you look at the animation on top, if we shine light through a double slit, last unit we learned that you get an interference pattern. These two sets of waves interfere constructively and destructively, and you see that pattern of your central maxima, and then they go left and right symmetrically to give you these lines, or if it's a laser, you get dots. We saw that. Light's a wave. That's a wave-like property. But if we take particles, like let's say we got a bunch of baseballs and we throw them through two openings, let's say two doors on a wall, what happens is the baseballs come flying through all different directions, it just kind of smears in the wall. It doesn't act like a wave. All right, so we're stuck here. You can go through one slit or the other slit. You can't go through both slits. You can shine a laser through both slits, but you can't throw baseballs through both door openings. It goes through one door or the other, and there's no interference on the other side. There isn't a large baseball in the middle and then smaller baseballs going to the right and smaller baseballs going to the left. It doesn't happen. So Davis and Grimmer say, well, we've got to dial this down. Baseballs aren't going to work. Let's try something else. So let's try electrons, because electrons are 10 to the negative 11 meters in our little example here. And let's push them through, not a double slit, let's do a diffraction grating, because it's too hard to double slits. So this is a cathode ray tube, which is your old TV tubes that you have when you were a little kid, not the flat screen TVs. You have an electron gun in the back. You shine it through some double slits, which in this case would be your diffraction grating instead. And that would be a crystal lattice in this scale. So you take a tiny little crystal lattice, you shine it through, and what happens? Well, in the X and Y direction, instead of having a central line and working out, you kind of see in these circles here, these little concentric circles, bright and dark and bright and dark and bright and dark of an interference pattern, both in the X direction and in the Y direction, and in between due to the crystal nature of all this. And if you do that old equation that you've had before, lambda over D equals X over L, everything fits perfectly. But these little electrons that you and I know are particles, or little blue balls with the minus signs painted on the side of them, they're now displaying wavelength properties where they interfere when they hit the TV screen on the front and cause this little phosphorus screen to glow. They're glowing as if they're a wave. There was actually kind of like an interference pattern between these electrons as they go through. So this is one of those, boom, mind blown here, that little electrons are acting like waves. Now, if little electrons can act like waves, so can protons, so can neutrons, therefore so can atoms, then molecules, and you work your way up to you and me, or a baseball being thrown from the mound. We're going to have wave-like properties. Crazy. If you want to know just a little bit deeper of an explanation, because I really simplified that down, what he did was he had an electron gun, and another way to do this was, besides what he did, or what those two guys did, was hit a nickel crystal target, and the nickel crystal target is too thick, so it bounces off and it hits a deflector. And in doing so, so here's your nickel crystal, the electrons come in, and you shoot an electron and it goes bouncing off. Then you take your detector and you move it up and down and around, and then from that you detect these electrons that are coming off, and as they scatter off, because it's kind of like hitting a diffraction grating, instead of going through though, they bounce off. They're going to bounce off. When they bounce off, they give a scattering pattern to this, where it kind of looks like you can see peaks and troughs up here of the graph, the number of electrons at the angle, and that's your classic double slit experiment. So the mathematics worked out better for this one to actually see it come into play. There's a neat simulation you can do to go ahead and shoot electrons at a crystal and you see them come off, but I wouldn't take your time doing this. It's just something that kind of shows a neat little sim that's out there and exists to make this work for you. So at the end of the day, when we look at all this thing and we move forward, what are we seeing here? Einstein in 1905 says, you know what? Waves, light, have particle-like properties. So waves are both, light is both a wave and a particle. Then you get into 1920s with deBroglie and then Davis and Grimmer coming along saying, well, you know what? If waves are particles, then particles must be waves. And that kind of brings us full circle around to this whole thing, which is just absolutely crazy to visualize what's going on. All right, I need to get out of this. I need to stop our recording here, and we're all set. Take care, guys.